Hi everybody. Today we're going to finish up our video series on the Qbot malware by putting together a number of techniques we showed in the previous videos in order to extract and decrypt the embedded network configuration in Qbot. We're going to work this on two samples, both shown in previous videos. One as the older kind of original style of Qbot, and one is a newer variation that came out recently that updated the encryption process just a little bit. Both the example hashes are in the video description, so you can download from malware.com in order to practice on your own. We're going to start this video just by describing the general process of how Qbot stores the network configuration, then we'll demonstrate the technique, and then we'll finish up the video by digging into the assembly for the newer variation that updated the crypto process to show you how to find the cryptographic operations in assembly so you can see how to basically what the changes were and how to recognize the changes if they make new changes in or new modifications in future variations. So to start with, let's go over how the configuration is stored. So for both variations, the Qbot's going to store the configurations in the resources. Generally, there'll be two resources, one smaller one and one bigger one. The smaller one has kind of campaign information. The bigger one has the network configuration. Both the configurations are stored in RC4 encrypted, and then all you have to do is be able to determine what the key is to decrypt them. That's the big difference between the two variations. In the first variations, the key is the first 20 bytes, and that'll be your RC4 key. In the second variation, the key can either be the first 20 bytes, just like in the original variation, or if that doesn't work, then it'll be the SHA-1 of an encrypted, usually PowerShell path string in the Qbot malware. So in order to extract these resources, you're going to have to unpack Qbot first. So there could be any number of levels unpack and depend on the variation. So I've seen it usually between like 1 to 3 levels unpack it. In our first video of the Qbot series, we went over how to quickly unpack the malware. So I'm not going to repeat that process. And the examples we're using here are the final payloads. But in general, just keep on unpacking it and then check the resources at each level or each layer. If you see those two resources, then you can test out the decryption process we'll highlight today. And if they decrypt it, then you know you're good to go. The other thing you want to realize is the configuration can be stored either in the ASCII dotted decimal notation, where you can just read off the IP addresses, or in the binary kind of network format. If it's in the binary format, it'll just have 4 binary values for each octet of the IP address, followed by the port number in big endian format, and then you'll have a basic separator character. In the case we're using here, it's going to be the binary value 0, 1. So all you do is look for either a repeating separator character, or you look for common ports that you recognize in hex. Like 1 Bravo Bravo is the hex for 443, so that's a pretty easy one to look for. So with that out of the way, let's go ahead and demonstrate how to do this on both variations. So we're going to take sample 1, open up in Resource Hacker. Again, this is the final payload I've already unpacked. We see there's 2 resources, a pretty small one, that's the campaign information, and a bigger one, that's the binary or the configuration binary resource. So right click, save resources bin, and we'll call it 311.bin. We're going to open this up in HXD. And no matter the variation, we'll basically try this format first, as we'll take the first 20 bytes. In fact, before we do that, we'll copy them to Control C, and then we're going to open up we'll open up CyberChef. And then we're going to do RC4, and we'll paste our key in there and change the format to hex. Now we go back to HXD, and we're going to do Control-Shift-N, and we'll copy that. And you can see if we scroll up to the top, so we're copying after the key, so after the first 20 bytes. We paste that to the input, change the input format to hex, and we see our dotted decimal notation of the IP addresses followed by the ports. Notice 443 is used numerous times, so that's why that's always a good one to recognize in binary. Now you see these first 20 bytes or so that look like kind of garbage data. That's actually the SHA-1 of the configuration that Qbot uses in order to validate the decryption work. So basically for the newer variation, it's going to go through the same process, try to decrypt it. If it fails, after it tries to decrypt it, it'll compare the hash to this first 20 bytes to see if the SHA-1s match. If it matches, it knows it decrypted it correctly. If it doesn't, it needs to update the key to a PowerShell or the SHA-1 of the PowerShell path stored in the encrypted strings. So we're going to walk through that process next, but you can see for this earlier variation, how simple that is. It just, the RC4 keys is stored encrypted, so there's nothing more to it. So let's go ahead and delete all this so we don't get confused while we're doing the second sample. And now let's do sample 2. So we'll pull this over Resource Hacker. We see 2 resources again. We see a moderate sized one and a small one. So the small one is the campaign information. This bigger one is the network configuration. So we're going to right click, save resource to bin file, and we're going to call this 3719.bin. Open this up in HXD. Again, we'll take the first 20 bytes. We'll copy those off, put them as the RC4 key. And then we'll take the next bytes, do Control-Shift-N, copy them as the input. And we see that we don't get the IP address and the dotted decimal notation, but maybe it's in the binary network format. Let's do a 2 hex dump. And now we're looking for the 1 Bravo Bravo for 443 or any repeated character for the separator. And I'm not seeing any of those. So it looks like it didn't decrypt. So I'm going to delete our key so we don't get confused. Delete our hex, and we'll turn off this hex dump. I'm going to open up one more CyberChef because we're going to need this for, and we'll open up as SHA-1, so we're going to need this for the new key. So first we need to get the key. So in this case, and currently, it's going to be the PowerShell path stored in encrypted strings. So all the strings are stored encrypted. In the last video, I showed how to automate the string decryption, so I'm not going to review that process. I also provided a script and showed you how to update it for different variations. So if you want more details on that, just watch the previous video. So I'm going to go ahead and hit the play button, go to AGDC services, and run my string decryption script. And you see at the bottom, I get all my strings. And in this case, the string came at the very bottom, and so I could see in the screen. But it's going to be the PowerShell path, the full path. So I'm going to Control-C to copy that. And then I put this as my input. And the SHA-1 of this path is the key. So I'm going to copy that, go to the RC4, and paste setting as my key. Now I need to go back to HXD. And it looks like I closed it. Go do the 3719. Sorry, missed the HXD, so we'll just drag it over there. And so in this case, because the first variation didn't work, we know the first 20 bytes is not the key. So instead of skipping 20 bytes, we copy the entire resource with a Control-A and then Control-C. We paste that in the input. And now again, you see we don't see the dotted decimal notation, but that doesn't mean it didn't decrypt correctly. So we're going to add that hex dump back on. And now when we're looking at this, we see a 1 here, a 1, a 1, a 1. So you see how, the 1 here, the 1s are repeated. That's our separator character. And we also see 1 Bravo Bravo, 1 Bravo Bravo, 1 Bravo Bravo, 1 Bravo Bravo. So that's a 443. So this one decrypted okay. So these, you just have to remember these first 20 bytes. 1, 2, 3, 4. That is the SHA-1 of the payload used to validate that it's decrypted okay. Then we have the separator as this one. And then we have a 4 byte IP address. And so each value is the octet in the IP address, followed by 2 byte port, followed by the separated character. So let me highlight this and we'll show this in Python to see what it is. I'm going to go ahead and open up Python. So this is going to be hex of 2 delta, 2 echo, 35, 8 Charlie. Sorry, hit the typos on all these. And then the port is going to be 8 alpha echo. You see the 8 alpha echo is just the next 2 bytes there. So on some reason the enter key is not working. Let me see what happened. Print. There it goes. All right, so I'm not sure what's going on there. So you see this is going to IP address, the IP address up here, and then the port 2222. So pretty simple to recognize once you realize it. Just make sure you understand that it can be stored in either format so that you don't decrypt it, get kind of a blob like this, and think it's not actually decrypted correctly. So always look at the hex dump and then kind of verify to see if you see there's 1 Bravo Bravos or any separated character like the 1 value in this case. So it's pretty quick to extract those resources. Takes a little bit of time to decrypt it. If you need to get the key, it might take you a little bit of time in order to update that decryption script. If for the variations you're looking at, if they changed it. But all in all, you can probably do this in 30 minutes and get all these values and get an exact listing of everything. And actually, you can do a lot quicker time once you get some practice on it. So now that we showed how to basically perform the process, let me show you how to find the encryption in assembly code, because right now we're using this PowerShell path, but what if they update that PowerShell path and they use a different string instead? We still want to be able to find that in code to see what the new string is. We don't want to rely on just using the tricks. We want to understand the tricks so we can modify it as needed. So in order to do that, let's talk about the process of how Qbot decrypts the embedded resource. So to basically it needs to decrypt the resource string, extract the resource, and decrypt and verify resource, which basically consists of RC4 decrypt, validate hash, and repeat decryption process with updated key if validation fails. So by understanding that process, it's going to help us find this in code. So we know what the resource values are because we have unpacked and we can see them in Resource Hacker. So in order to find these general steps, and they're going to all occur basically next to each other, we're going to look for the resource string in the encrypted format. So let's go down to here. So in our encrypted strings, I scroll up and I see 5812 and 3719. So these indexes are basically the indexes pushed on as the argument because the strings are stored in a big configuration block. And so at offset hex 491 is a string 5812. At offset 496 is a string 3719. So they're going to search for those in order to find the basically that find resource or location. So I'm just going to hit Control-Shift-E. I'm going to search in my instruction operands, and I'm going to do the first one first. So 0x 491, and I'll do search all. And we have one instance, so I'll select that, hit the graph mode, and here we decrypt the string. That means these next two are going to be something to do with the resources. So I'll label, call this resource stuff. I'm not even going to look at them to see what they are. Resource stuff. But because we have two resources, I just want to be able to recognize. In fact, I'll put that one, hit L to rename again as a 0. I just want to be able to recognize that these are called in the second one too, so I know I'm in the right location. Once we extract the resources, we go into our if block, and then we decrypt the updated key. So we can see here it's the PowerShell string. And then that means the following function, we'll hit L to label. This will be decrypt and verify resource. And so that's how you find the general location. And basically whatever the string is at this location, that's going to be the SHA-1 of that string will be the updated key. That's at least with if they just make minor changes to the process. If they make more major changes, you're still going to be looking for where they extract the resources, but these next few functions could change. But if that'd be a complete change of the methodology, so then that would take a little more reversing to figure out. But this is a good general approach because if they make a quick change like this embedded string, you can easily find it. You don't even need to do any more work. If they make a bigger change, you can basically find this general location and then reverse it from there, without needing to go through all the code, because Qbot is relatively complicated to reverse engineer. So I labeled this as Decrypt and Verify resource, but if we double click it, we can see there's a number of embedded functions, and we don't really know where the decryption and the SHA-1s occur, so I won't be able to find that too. So we're going to look for RC4 and basically the validate hash, the take the SHA-1, in order to find those locations in the embedded, like the child functions, so we know we're in the right location and that I didn't just pick a wrong function. So we're going to search for SHA-1 first. SHA-1 is actually super easy to find. I feel like let's do it in the notepad so you can see it. So SHA-1 constant, or we'll call it magic constant, starts with, so it's going to be, we'll just put it here, it's going to be basically 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and then they do some more countdown. But they're going to do this in basically 4 D words as little ending. So we're going to search for 5, 6, sorry, not 5, 6, 6, 7, 4, 5, 2, 3, 0, 1, because we're searching for that basically 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So we're do this in D words, and then I'll show you the rest of it inside the file. But we do in D words, and each D word will be little ending. So we took this first D word, convert it to little ending. We'll do Control C, and then we'll paste that into the search and do a search all. So we see there's only one occurrence. So we click that, and then go back to the graph view. And we see here's the magic constant. So again, reading these in little ending, it's building it 4 bytes at a time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, F, E, D, C, B, A, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and then F0, Echo 1, Delta 2, Charlie 3. So anytime you see that, you can use something like find crypt Yara to search for it. You can just search for it in the search just in Ghidra if you know it. But once you find it, you know this function is going to be put out a label and call this crypto SHA-1. So the next thing we want to search for is the RC4. So again, if you want to understand, so I'm not going to go over how to recognize RC4 very in depth. I'm just going to show you very briefly, because the first video I did in my YouTube channel had how to reverse engineer RC4. So if you want more details, watch that video. But basically, RC4 builds a S box, a substitution box, with the identity permutation. And if it's, so we can search for that, because the identity permutation initializes the S box to the index of going from 0 through 256, or 255, so 0, 1, 2, 3, 4, 5, 6, all the way up through 255. And you generally have the hex 100 constant where it sets as a limit. So we can search for 100, but there's a number of false positives because 100 is a relatively common hex constant. The other thing we can search for, which only comes up maybe half the time, is if RC4 saves the state information. It'll almost always save it in the at the end of the S box at offset 100 and hex 101. As we mentioned, the 100 is overused, so it's not the best one to search for, but 101 is not that common. So we're going to go and we're going to search for the hex constant 101, do search all. And so here I'm going to look to see which ones make sense. So 101 Charlie's false positive. So here we're grabbing out the register with plus 101, which would be potentially the S box. Let's see if we're storing one. Here we're storing a value into register plus 101. I'm going to click that, go back to my graph view. You see here we're storing 100 and 101. And we have basically a loop with an XOR loop. And then we have the 100, 101 beginning. So that's basically the pseudo-random generation algorithm, because we grab the state information, we perform the encryption or decryption, and then we store back your state information. So that's pretty easy to recognize. Go ahead, out a label, call this crypto RC4 PRGA. In order to find the key scheduling algorithm, I'm going to find the cross references, Control Shift F, And I know I'm looking for a location that we have the RC4 decrypt followed by the SHA-1. And since we already have the SHA-1 and the PRGA of the RC4 decrypt, the KSA or the key scheduling algorithm is the first function. We can just look for the location where that occurs. So I'll go to this first instance. There's no SHA-1 after it, so it looks like a false positive. And this isn't guaranteed to always work out this nicely, but most of the times it will in this Qbot malware. So go to the second one, and again, no SHA-1 after it. We'll go to the third cross-reference, and here we have a SHA-1. So let's go before it, and I suspect this is a KSA. I see my hex 100 constant, which is used as a bounds for this SBox permutation. This is the part, if you watch the previous video on RC4, should scream RC4. We're initializing a buffer to our counter, which gets initialized to 0. So basically going 0, 1, 2, 3, 4, all the way up through 255. So that is a pretty big giveaway. And then we come down here and we basically jumble up the SBox based on the RC4 key. So we'll hit L to label, call this crypto RC4 KSA, Alt left to get back. And we can see, so now we're going to go through the rest of this function just to identify the function so we can kind of talk about what this is. Because again, if you get a variation that just updates a string, you already have more than enough information in order to update your methodology. If they update the crypto a little bit more, then this will give you a better idea of how it works. And so you can update your algorithm without having to go through the whole Qbot. Let's go into this first function and see what it looks like. So this looks like it does a memcopy. We're grabbing from one buffer into another buffer, and we're doing that for ESI times. We're going to go ahead and hit Alt label, call this memcopy, Alt left to get back, come down to here, and this is a pretty standard format for a memcompare. You take 1 byte of a buffer, you compare it to the other buffer. If you're not equal, you exit out. If you are equal, you loop around. Once you're done, you basically take 1 byte and you subtract from it the other byte. And that means if they match, you get a 0. If they don't match, you get either 1 or a -1. So we'll hit Alt label, call this mem compare, Alt left to get back again. So this whole function, we'll hit Alt label, call this crypto decrypt and validate hash. So we're going to do a memcopy to basically extract out a part of the payload or the configuration. We're going to decrypt it with RC4. We're going to calculate the SHA-1 on the decryption part. And then we're going to compare that to, you can see 14 hex bytes or 20 bytes, to the embedded SHA-1 of the payload to see if they match. If they don't match, we return a -1. If they do match, we copy out probably the payload part specifically. So let's go ahead and follow the cross-references and make sure we're in the right location. Control-Shift-F and go to the first cross-reference. You can see here, we call it twice. So we're either going to call it with this ESI plus 400 is going to be the first key, or we pass the second key to the other instance. So the fact we only had 2 cross-references and they're both next to each other where you take one path or the other, this is based on which key you're going to use. So this whole function, so let me go up to the top here, Alt label, and call this crypto decrypt and validate hash. And we'll follow the cross-references again. And we can see we're in a pretty small function here. And we'll just follow this one more. And we see this is already labeled decrypt and verified resource. So we'll follow it one more time. And we see we're right back up to the original part where we have our PowerShell string. So it's pretty simple, as you can see. So if you just need to extract your network configuration, all you have to do is unpack it, check the first methodology. If that doesn't work, just run the script that I showed in the previous video and have in the GitHub page, extract this PowerShell string, and then you can decrypt the variation. If that doesn't work, just go ahead and find this location in code, see if they updated this string, and then try it with the new string again, use the SHA-1. If that doesn't work, then you basically dive down into the actual encryption process and see if they made any updates. Maybe instead of SHA-1, they'll update the hashing algorithm. Maybe instead of RC4, they'll update the crypto algorithm, things of this nature. But now you understand how both the original or the earlier version Qbot and the most current version of Qbot store their configurations in an encrypted manner. You can easily find them in code, you can extract them and decrypt them, and you can update the methodology as Qbot makes changes. So I hope you enjoyed the video today. If you did, please like the video and subscribe to my channel to get notified when new videos come out. I also love knowing what you think, so leave me comments below. If you want more reverse engineering tips, follow me on Twitter. And if you're interested in structured training, check out my website for the malware analysis class that I offer. Until next time, keep on practicing and try to learn something new every day.